There we go. So I'll talk to you a little bit today about hardware engineering. So I think last time, was January or so, John Baker was up here talking much more on the software side, let you know what's going on in firmware and dashboard controller and such. So a little more focus today on the hardware here, and then we got some more after this. So a little bit about myself. I came to Meraki about over 5.5 years ago. I started talking to the founders in late fall of 2006. So I joined in early 2007 and been working on all the hardware products since then. Before that, I was at Apple working on notebooks, making computers just like a lot of the ones I see here. Never suspected to see this many Apple notebooks in a
the number has been rapidly rising in the last few years.
Yeah. Well, when I joined Apple, it wasn't like that. We were much more of a scrappy company. But before that, I was actually also at Applied Materials, and that's in the semiconductor fabrication. So working in fabs, working to get some of the latest and greatest silicon out there. So I've been on kind of the ends of the industry in electronics on the silicon side, and then moved into the client side, and now into the networking gear. So it's very exciting. I love making new products. So I'll talk a little bit briefly about our product design, kind of overview of that, and then go into a little bit of conversation about how we've solved some of the challenges in building some really great access points, and then how we ensure quality and reliability as a result of that. So first off, this is a highly simplified approach to how we develop our hardware here at Meraki, and I've also added a nice little blob on firmware. That's nice and simple little aspect about making an AP. But after we have kind of that product requirement stuff, we have to go figure out, okay, what kind of silicon we put in here, make that architecture, and figure out what all the detailed specifications that are on the hardware. And then we start our design. And that's a very complicated and concurrent type of process where we're iterating on the industrial design, working on figuring out the board electronics system, the SoC, the RF front ends, and integrating that with the mechanics. And it gets really messy, but it's a very exciting time. And then on the output of that, you come out with a great design, and then you go and you do a few iterations of build. So we test and see if we can validate against the performance specs we want to achieve. And we do that 3 times. This model of how to develop something like this is very common in the electronics industry. It's something that Apple actually uses very much so. And a lot of the same principles in how to build a custom device are applied here. So Meraki is not alone in this, obviously. There's a lot of technology partners that we rely upon. And you'll see a lot of familiar names up here. Surprisingly, these are all nowadays what we call fabless semiconductor companies for the most part. But they're able to, these guys are really the best of breed for the networking industry. And we're working with these guys. And it's not just one that we're going to be going to say, hey, we want to make an access point. How do we do this? No, sometimes we actually have to put together some of these solutions that they've designed. And we're going to work with them hand in hand throughout this process to make sure that we come out with the best design we can. So on the radio side, we're working with Qualcomm, Atheros, Microsemi, Skyworks, and some others. And then we also have these other products as well, like switching and appliances. There's several other companies up there, but these are just a few that are applicable to what we're talking about today. So quite simply, we start out with the radio design. We start with that silicon, and you see there the 2, 4, and the 5 gigahertz radios. Got a few props here. I'm going to hand this around so you can see it a little firsthand while I'm talking about it here. But this is an MR16, dual band, dual concurrent wireless device. You get a closer look there and go ahead and pass it around. And so we start with these radios, and that is really that plus the source code, and that's the contribution that we're going to get from, in this case, Atheros or QCA. And then
do you do any low-level coding on the chipsets?
Certainly, in terms of we've actually been a partner with Atheros since 2006 or so. And in fact, our founder's been programming with the Atheros source code even prior to the founding of Meraki. But one good demonstration is that if you want to do mesh networking, you actually need to write and modify the drivers, and that's very low level. And then you have in the kernel and the Linux a lot of other applications that have to pull that off. But certainly, that is absolutely essential. Great question. And so, moving on to the transmit side of a radio, right? When the radio is talking to a client, we go ahead and actually have to modify and use an external, what we call an external front end on this. There actually is a way to connect just that silicon to antennas essentially, and have very simple radio design, but we don't use the internal transmit and receive functions within this radio. We actually use the external connection to it, so we bypass the internal function of that chip, and we add this on. And so that customization is very, very sensitive, and that has the most to determine what you're going to have on your transmit power. So we tune these radios in enterprise settings or in this application so that we can get the maximum power within the FCC limits. And FCC mask is a little complicated, but because there's rules about all the different channels and such. And even FCC is not the only regulatory body that we're designing to. We have to think worldwide as well. So those, you see, this is a 2x2, so you see 4 distinct front ends on this. Now I'm going to show you here.
Are you actually?
There we go.
I know Athros has a reference design for their chipset, so you're actually making this specifically for your MR16 radio and altering the design from the
certainly
reference design.
I grabbed this on the way up here. Something like this device here is what their reference design looks like, right? And so there's certainly we have to work with them quite a bit to make this design happen, but this is a very Meraki specific front end. So our filters, our PAs, our LNAs and such like that is all tuned for this particular design.
Okay, very interesting.
And that's where a lot of this iteration happens, because you have specs up front. You say, hey, I want to get these transmit powers on these channels at these bit rate selections, and then you go through and you measure in like an EVT phase, that first validation test, you might not achieve those powers you're looking for. And you have to go iterate on this, and so that takes time. And we're not just working with Atheros on that, because the key silicon on the front end are actually these power amplifiers. So that's where you're working with players like Microsemi or Skyworks, right? And then similarly on the receive side, we have to do something very similar, in terms of filtering out the signals we don't want to listen to, and make sure that we can hear better than like that standard reference design. And then a few more things here is that when you're working with dual concurrent radio, you basically have these 2 powerful radios in a little box right next to each other, right? And so it is very common that if you don't design against it, you can have one radio that interferes with the one right next to it, right? So we have to take extra precautions to make sure we don't have any of that crosstalk. Sure.
Can you elaborate on any of that at all? Because I see when I have a 5 gigahertz client connected and I start passing traffic through with another client connected on the 2.4 gigahertz, my 5 gigahertz client is starting to suffer in terms of performance.
Mm-hmm. Yeah, I think we go through a lot of testing in terms of fairness and having just multiple clients doing throughput tests on different channels and such in the settings. So I think I'm not sure exactly what you're seeing there, but certainly we could file a ticket with support and take a look at what you're seeing. I think there's many different things that could be happening, but that is specifically something we want to make sure we don't see. So one of the other things I want to point out here is, even though we're partnering with some of the best of breed in the silicon side, right, there's always going to be some kind of bugs in the hardware or in that source code that we're working with on that low-level driver settings. And so, and this is very low level just with respect to radio, transmit packets, signal strength, and that type of stuff. So one example is, like, I think on the MR24, we had kind of what we call a spurious emission. So one radio was actually unintentionally broadcasting at a frequency, I think it was a 2.4, was broadcasting some 5 gigahertz signals, which were being picked up by the radio next to it. So we had to put in filters specifically to address that one issue. So that's something that you actually validate and test, through net cycles, because you weren't expecting to see those. It's not as advertised, but you have to be able to detect those.
You're talking about before you release this AP?
Yes. Yeah.
Okay.
That specific issue was with an MR24 in specific.
Okay.
But that's something we detected really early in our vetting in this process. And then also, we oftentimes call upon firmware to help us out because there may be some settings that need to be adjusted because we're covering up for the connection to the PCIe bus or something like this. So there's a lot of workarounds that need to be ironed out there. And one other thing I'll point out here is that you all hear about the, bandage possibly, like channels 1 and 11 aren't as good as or powerful as channel 6. So that's something we want to make sure we address also in that, there's limits in terms of at the very edge in channel 1 and right below, in the frequencies right below channel 1, there's the FCC has restrictions. Don't, broadcast too high of a signal on those frequencies. And so, unfortunately, if you have a bad RF design, you'll have to turn down your radios on those channels to pass the FCC requirement. So that optimizing for the bandage, that's what you see here in these charts here, is that we're paying close attention to the channel 1 and 11 to make sure that we can keep the powers where they need to be and also pass a specification. Here's a little bit about antenna design. So you've probably seen from excuse me, our website. This is an MR24 here. This antenna array. So this is what we're seeing here, and the design of this antenna is a very iterative process. So we start out with, hey, what do we want to achieve from a product? It's an internal antenna. We've got this thing that we want to mount on a ceiling or a wall. That's where we want good performance. We've got 6 radios, or six chains that we want to support. We have 6 antennas that we need to put in this little box, which is a little bit of a challenge. So we work with the guys who made a lot of these antennas, and we have an approach where we go and model our device, which you see here on the left, a little dark there. But essentially, it's a ground plane and a mocked-up enclosure very early on in the device. This is even before we do our first board spin. So we get to work on this type of modeling, and you put it in a chamber. And then every step of the way, you go and you modify and tweak, because the effects of like the PCB, the enclosure materials, how far away these things are from the antennas, they all have a big impact on the efficiency of these antennas. So we usually use PIFA antennas, because these are typically give you the best efficiency, which really means when the radio generates a signal, it propagates that signal in the directions you want it to be, and how much you get it in the direction you want it to be is kind of your efficiency, and that's what we're really focusing on. Okay.
Can you just comment on, you have a very similar design as Arrowhide in regards to antenna and positioning.
Yeah.
Can you comment on how do you differentiate between each other?
Yeah, I think a lot of it is in regards to how it's tuned for this particular enclosure. There are other designs.
Or hardware-wise, or both?
Excuse me?
Software, hardware, or both?
It's always both. And in this situation, having 6 antennas in this kind of a circular orientation, it's actually getting more and more common. We were actually the first to release, one of the very first to release a 3x3 enterprise dual band radio, and this is that product. And so I believe we were the first on the market with this antenna array. But this type of approach is being commonly used elsewhere because it's very efficient. And PIFA antennas are used pretty much throughout the industry. Sure.
Is it a 3x3x2 or 3x3x3?
3-stream 3x3.
3x3x3.
Yeah. So
it's
3x3
compared to Arrowhide 330. So
yeah.
The board looks.
Yeah, and since you're working with multiple antennas, some of the plots you see down there, you see the gain by each antenna. You're tuning each antenna relative to the enclosure, not just like one big measurement. So.
Are these your engineers that are working on the antenna designs, or are you outsourcing that to another firm that specializes in antenna design?
We're using a specialized antenna vendor, not like an ODM, the actual antenna vendor. So, and oftentimes what we'll do is we'll go and we have a Rolodex of several different companies, and we'll evaluate each of their approaches to the design. And that way you have people that are constantly fresh with the latest, greatest technology. Talk a little bit about mechanical design. And first and foremost, I'll try and speed up here so we have enough time. Talking about industrial design. So the design of Meraki's AP, this is all done in-house. The concept, and sometimes we'll work with a third party for industrial design, as an industrial design firm or such. But for the most part, we do all these designs in-house, and then we go and apply a similar model where we design on paper, put it in a CAD, and then we go mock up and we start iterating and testing. So that's what you see here, the SLA model. These are things, rapid prototyping. Then you move to machine tooling, and then or machine components. Like you take a big block of plastic, you machine out apart, and you test it. You give it to the guys who are working on the antenna, and use that so they can use that to test. And it's very helpful throughout the whole process to have these models. And then we also move into hard tooling and such. And again, we're working with best-of-breed vendors to make this happen. The fit and finish is something we pay attention to, because if you look here at MR16, that is this guy right here. It's pretty thin. And we packed quite a bit in this little package, so I think it's one of the thinnest on the market. It's about an inch thick. And so it's not an easy challenge, not an easy design to accomplish. But we pay very close attention to that fit and finish, the gaps, the offsets, the look, the color. All these things, they mean a lot to us. And it's because it contributes to the customer experience for Meraki. So look at, it can't just look good. It's got to be very durable, right? I'll show you some pictures here about some of the testing we do in the next slide. But we do run through a lot of reliability testing. So you see here an exploded view of our access point. This is the MR24 in this case. We have we call it plenum rated enclosure. And plenum rating is like this UL2043. And what does that mean? It means when you have a plenum in a building, which is this fire code area above rooms, anything that's in there can't catch on fire, cause smoke, and smoke out the rest of the office or so. And so how you pass, how you get rated as compatible with that specification is you actually take an AP, you put it on something that looks like a big barbecue, you burn it, and you measure all the particles that are generated. So I want to show you a video, but it'll take a little while. But it's pretty hard to pass this test. In fact, there's only one plastic that's made in the world that will enable us to pass this test. And it's a very expensive plastic, which makes that top component, that top housing you're seeing here, one of the most expensive components in the bill of materials, actually. And it's not easy plastic to work with. It's very angry plastic. But besides that, we also put the assembly together, and we focus a lot on the usability. So we see what it's like to mount it on a ceiling, on a ladder, mount it on a wall, mount it on a T-rail kit, mount it above the plenum. If it's an outdoor product, mount it on a vertical pole, a horizontal pole. And so how to ground that device. So these things we pay a lot of attention to. So we do a lot of iterative, testing on that to make sure it works well. Even in the box, we include everything you need. We have a template for what the holes are on the mount plate, so you don't even have to look at the manual, because most people really don't read the manual anyways.
Thank you for including stuff like that. Stuff like that makes it easier to give to installers and make sure that it's done right. And I know Pablo loved my ceiling after the last field day of having actually tested everybody's drop ceiling mounting kit and figured out how long it took me to mount, and your guys were one of the quickest.
Great. Appreciate the feedback.
And no one else could do that because no one has a drop ceiling in there.
What can I say?
He also has a plenum and a barbecue.
I'm thinking about a new testing idea now.
Yeah.
My wife might kill me.
Here's I was mentioning about some of the testing we're going to do. Not only do we test just the enclosure, dropping it, but test what is drop 10 of them in a box, make sure it gets there, delivered to the site in one piece. Do a vibration test. These things are stuffed on airplanes. They're subjected to vibration. We learned a lot about this stuff, and I was working for Apple. Cables would come loose, on a laptop and causing 1 in 100 failure. So a lot of things I applied here. Outdoor AP durability. Here's one thing that's interesting. You look at outdoor products. We've been making outdoor products for a number of years, and we know that in coastal environments, that the salt in there is very corrosive. And so aluminum doesn't like to be exposed to the elements on the coast. And so it quickly corrodes. And cast aluminum, what's used in these APs pretty much across the industry, it's very porous as it is, as a metal. And so once you start eroding it, you drive these pores even bigger, and eventually it starts leaking, and then it causes a failure. So what we do is we actually apply a coating to these to the aluminum chassis prior to painting, so that undercoat, I guess similar to what you might put on a car, gives it that durability, so it'll last for a number of years. We also, you can see some of the testing here, the salt spray tester, where we actually do the accelerated life testing. Another test we do is for IP67 certification. You got to dunk an AP 1 meter below water, and then bring it up and verify that it works afterwards. And so this type of water ingress testing is pretty valuable. And I think going that extra mile to ensure that these things will survive a very big storm or such is important.
I always wonder with that test, you know, how many people would be actually mounting APs 1 meter below water?
Florida.
If they're in a flood, then unintentionally they may have, right?
Actually, this would be the friendly environment.
Another test, so thermal testing. Not only do you want to just test the thing in a wide range of temperatures, put it in a box, seal it, and then test it. And then that's something I think is going a little extra mile. Make sure that while it's sealed, it's not getting an airflow, that each of the components you see on the upper right, hooked up to a little temperature monitor, is not going to exceed the threshold that it would cause it to have a really reduced life.
Do you test it to very low temperatures as well?
Yeah, these are tested to like 0 degrees C operations, and then you can go further, but it's all about you want a cold boot and things like that.
Do you have any APs that like have internal heaters for really low environments like ski fields, those kinds of things?
Yeah, we haven't. There's not much demand that we've seen for that, so we haven't really designed that in. It's certainly very possible. Sometimes in very low temperatures, that people will put these things in another type of enclosure because they've got other effects like icing and things that they're worried about.
Like a heated Nemo enclosure.
It's actually quite popular. Most of the outdoor solutions that are focused are rated up to minus 40 degrees Celsius.
Mm-hmm.
Because it has the, as
Yeah.
you said, it's not the operational that it's the problem. It's the boot up.
Yeah.
Right? If it's cold, but most of them go to up to minus 40.
Yeah.
We do have the hardware watchdogs and all that stuff as well.
Yeah. Customers will do certainly a lot of. I mean, we have these things in ski resorts in areas that are very cold, and they certainly do operate at very low temperatures, and you know, and I think also there's other APs where we can offer at even a higher, you know, probably a higher price point because you have to go industrial rated everything across the board. Okay. Lastly, I want to talk a little bit about quality and the programs we run here. Most importantly, quality is designed in from the start. And these iterative tests that we do is absolutely essential. We have to analyze every single failure when they occur, whether they came right on the manufacturing line or if they came 2 months later when a product's in development. We study every failure, and that's absolutely essential because if we don't, those problems are going to recur again. Second, quality components. So not only do we make sure we have done quality checks on the components coming into a factory, but also where they came from on the outgoing on that. We actually do quite a bit of inspections. And we work throughout the supply chain to make sure the quality controls are in place and something to our standards. During the factory assembly and testing, 100% testing in all radios. Actually, it's usually 2 and 3 times testing per radio. RF calibration, throughput tests of different types with directly conducted or through the over-the-air wireless test. All these things are very important. So you get multiple times to detect any type of an early failure on the line. And then we also do sampling once we, products come off the line, we randomly pick those, put them on a test rack. We actually have a remote inspection process. These things are connected to the cloud. It's very easy to run a remote diagnostic and verify that yes, all the radios are operational. It's downloaded the latest and greatest firmware, and we get a very good preview if there's going to be anything that could be of a challenge on that build. Also, once a product's in the field, after we've released it, for the first quarter or two, we're actually taking a look at every field return to make sure that we have found in that development process every type of issue that we could see. And those early field failures that are actually very essential to jump all over. Again, this is a quality program that Apple does, and I brought it over here because it's highly effective. And you're having engineers study these things and not just a quality person. We're also looking at trends in the RMA so that after 2 years or so, or a year or so of production, we want to highlight if there's been any shift in any component quality or such, and this is where we can identify that. Things do happen sometimes. We also look at rolling reliability testing because in the factory we take random units off the line and we have them operating, not just for like a few days, but actually for months. and we continue to replace those units and put new ones in so that we're sampling throughout the production life of any one product and finding more than just that early failure, that early sampling. We're actually having these things run for months. And lastly, because of our firmware and how our cloud controller works, we're able to, the firmware team is able to analyze the thoroughness and effectiveness of their upgrades, make sure that any upgrade, if it does fail, they can detect that remotely. And also, they look at things such as a reboot frequency. So, if something were to happen to a system where it needs to reboot itself, we look at the frequency of that, and you can oftentimes figure out what happened in the history and the event logs, and so you can design in and improve the next iteration of the firmware. All right, so that's what I had for today.